So welcome everyone. So as I've told you that for today we are handling lesson 1. So very first, the lesson target, is only 1. Our lesson target for today is that we are going to simply we are going to introduce physical optics, and understand all the basics. Yeah. So the most important thing is that I am supposed to leave you with the heading progressive waves. Yeah. So the last heading that we should have should be progressive waves, because that's what you people mostly complain about. And by the time I reach it, most of you may be very tired, so you may not calculate. Yeah, that should be the last heading. And of course, so we never leave class without research and what? And assignment. So we are going to handle physical optics and make sure we understand all the basics. You're going to watch videos, you're going to ask me questions, so that by the time we begin progressive waves, we are ready, we know some terminologies, and we are good to go. So that even in the future, even if there are sound waves and we find very funny things, we don't waste a lot of time. Realize in sound, there are things that are disturbing, like those beats and Doppler effect. So when I talk about things of refraction, reflection, diffraction, interference in this very class, when I reach sound waves, that means I'll be referring you this side. I don't know if people try to understand. Okay, now I think we can begin. We have very good notes that try to bring out the introduction very well. Yeah. So, oscillation and waves. Basically, or always in physics, people confuse the two, especially the newbies of physics. By newbies, I mean someone who has just come into physics. People don't get what oscillations are and what waves are. They don't distinguish the two. But for us today, we are here to distinguish them in our very first class. So we are going to talk about oscillations first, and then later on, we are going to talk about waves. So make sure you pay maximum attention, because this is what is going to determine your foundation as far as this is concerned. Yeah. So oscillations are not much. What is an oscillation? They are saying that an oscillation, they are calling it a regular to and from motion of a particle about an equilibrium position. Yeah. A case in point, you people know what they call a swinging pendulum. I've already told you about this. I'll use this very thing, and I think I'm going to even share it after. Yeah. You all know it can be swinging like this. Then it can also be swinging like this. Like that. It can go this side. It can go that side, then it comes back like that. It can also come back like that. Hope people understand. That's one of the examples of what we call an oscillation, but there are terms I'm interested in. Yeah, as you know, usually we don't cram anything. So today I'm going to begin with what these people are calling. So you need to understand the spelling of this thing. People usually write it with double S. Make sure you know that it is single S and the double letter is double L. Okay, so this is Webs 1. Let me first secure our document. And this is Webs 1. So I want to first challenge some of my friends who think physics is easy. Let me challenge you with this thing of oscillation. And after challenging you, I want you to listen carefully. So I want to begin with this. After challenging you, of course that is our support. We don't mind which support you used. So after challenging you, the deal is simple. You simply listen to me. Even if I'm explaining the simplest concept ever, you listen simply because I defeated you here. Yes. So this is the bulb. Then it can swing up to that point. The same bulb and swing up to that point. So the questions I'm going to ask, if you really know them, then you're a good physics student. So I'm saying this is my bulb. So let me add on something. And what is that? This bulb can be at point A, then it can swing and go to point B, it can swing and go to point C. Now this is my question. I don't know if I will get a correct answer from any of you. That's now perfect. It is at point A, it can swing and go to which point? Can swing and go to point B. It can swing back like that. You get? It can swing and go to point C, then it can swing back. So that's what they call an oscillation. So when I go back to the definition, they're saying it is the regular to and fro. So by to and fro, this is what they mean. To, then fro. You understand? To, then fro. That is done. Now this is my question. They're adding on and they're saying about an equilibrium position. About an equilibrium position. Who can show me the equilibrium position in this illustration? You raise up your hand. Hey, who can show me the equilibrium position or the equilibrium positions in that illustration? Anyone to tell me in the chat before I give a chance to Joshua? Who can tell me? Who can tell me? Okay, no one is telling me. Someone is like A, B, and C. Of course. A, B, and C. C and B. Since it is at rest at those points. People having different answers. Okay, let me hear from Joshua. Yes, Joshua?
Good evening, Doctor and other guys. Doctor, I think I'm trying. It's that point. A. Doctor.
With a reason, with a reason. This is not a market that we are asking you for the price of cabbage. This is physics, we are asking for the equilibrium position. You need to tell us the reason why.
Hmm. Yeah. Because it is it because it is where the same the
Because
the
it is
gravitation
where the
force
what?
acting. The gravitation force is acting.
Okay, thank you for the try. At least you've tried. But I think you can see that in the chat, you people are having different answers. Different answers. Different answers at all. But I'm going to educate you a bit and tell you about the equilibrium position in physics because you're going to come across it so many times. Okay, yeah. To save time, I'll give a chance to only that one. But don't worry, there is another question coming. Yeah. So what you need to know about the equilibrium position in physics. So every time it is mentioned, this is what you're supposed to know. The equilibrium position is what they call, someone mentioned the word rest, and I really liked it. I really liked it. The rest position. I liked that. So what you need to know, by the time we talk of something being in its rest position in physics, we are trying to mean the resultant force on this body is just zero. That's what you should understand first. When we say rest, you should understand that resultant force, which is like that, on this body is a zero because it is just there at rest. All these ones are assumptions. And on a pendulum, so get this from me, on the pendulum, on a swinging pendulum, it is the lowest point. Yeah, that's what I wanted you to learn only. Yeah. So the equilibrium position is the what? Rest position. And for the pendulum or the swinging pendulum, it is the lowest point. Period. Period. You all know what we talked about. I don't want to go into the calculations part. That will come later on. But what you should understand as of right now, for a swinging pendulum, the equilibrium position is the rest position. And what does the rest position mean? At that point, the resultant force on this bulb is a zero. And what is it? On a swinging pendulum, it is the lowest point, and our lowest point on our illustration is what? Is A. Just that. And I will not exceed that explanation. That is enough for now. When calculations come in, or you can even add it on a bit and say that when resultant force of that body is a zero and it is at rest, its displacement, we believe it's not even displaced because it is just there. So its displacement is also what? A zero. And displacement is represented by that letter S. You understand? Rest position, resultant force 0, even displacement is a what? Is a 0. Very obvious. Now, after understanding the equilibrium position, I'll take you back. So you now know the regular to and fro equilibrium position and so on and so forth. There are things I'm going to ask when we move to the types. So let's go to the types. So our example of an oscillation that we are using to understand them is the swinging pendulum. Okay, now, what are the types of oscillations? We have those that are free, then we have those that are damped, then we have those that are forced. Get it? Then we have those that are forced. So even if I don't write that down, they may not ask you for the types. You need to know what is happening in each kind. So with oscillations, we know those that are free, those that are damped, and those that are forced. So what's up with these free ones? What are they saying? They are saying that the free ones, these are oscillations where total energy of the oscillating system and the amplitude remain constant with time. So we are seeing terms that are coming in here. We are seeing new terms coming in here. The very first term is total energy of the oscillating system. Then I'm also seeing amplitude. So let's assume we are having the pendulum that is swinging, and I want to know which one exactly is the amplitude. Let me begin with the amplitude. Who can unmute and tell me? Using that very diagram we have, you tell me where is the amplitude? Where is the amplitude? Because when they tell you it remains constant, you should really know. You should really know. So who can tell us? You either text or to save time, you raise up your hand and speak. Which one is the amplitude? Yes. Yes, little fairy. I think their network is very poor. Let me just check what people have said in the chat. People, there is nothing in the chat. You people, how can I get amplitude from my sketch? Distance from the fixed point to C. Anyways, one has tried, and I always want at least one person to try. So you people, what they call the amplitude, I think you can see, so please respect the introduction. Yeah, respect the introduction. Don't belittle any content. Okay, so what is that amplitude? The amplitude is the displacement we are going to have from our equilibrium position A up to this point C or this point B. You understand? Any of them. So we assume that that is the maximum point reached. So because it is the maximum point reached, that means it can help us get the maximum displacement attained. So it is the maximum point what? Maximum point reached. Just like even this one. Yes, it is the maximum point what? Reached. So that means from A to B, we have the maximum possible displacement. From A to C, we have the maximum possible displacement. And what you should consider in this case is vertical. You get? So you can see, you consider the vertical displacement. And that's what they call the amplitude. Hope you understand. So from here to there. Maximum amplitude, or just amplitude, yeah? Which is the maximum displacement from the equilibrium position to either C or D. So whichever statement you're going to read from textbooks or even from our very notes, you'll understand. They will tell you it is the maximum displacement from the equilibrium position to the farthest point that can be reached on either side. They can call it the maximum distance from the vertical position, which is also very okay. So don't be worried about it. Yeah. You find books, so many books, where they consider two cases. There are books that will tell you that this is also our amplitude. Yeah. But the good thing, what you need to know that today is not a day of calculations. Don't mind it. Because this is also a displacement from our equilibrium position to the what? Maximum or farthest point reached. You get it? Just because this one is horizontal and this one is vertical. So when they consider amplitude in either cases, just don't be confused. I want you after here, you can check Tom Duncan and then also check physics for today and tomorrow. You will see that either cases were talked about for amplitude, but you just wait for the part of calculation, then we'll understand. What you need to know, it is the maximum displacement from where the equilibrium position to the maximum or the farthest point reached by that body in oscillation. As simple as that. So amplitude, I've sorted you. So they are talking of energy of the system. You also need to understand the oscillating system is just simply that bob trying to oscillate to and fro. So when they talk of total energy of the oscillating system, you know those things of kinetic energy and potential energy. You studied these things, isn't it? If I may ask you for example, where is kinetic energy maximum and where is potential energy maximum? Who can raise up their hand and tell me where is kinetic energy maximum and where is potential energy maximum? Yes, Engineer Joshua.
At point C and point B, kinetic energy is maximum.
That is
Then at
wrong.
point,
Why is it maximum? Are you sure kinetic energy is maximum there?
no, doctor, from point A as the ball is in motion to point B, kinetic energy is maximum.
Kinetic energy cannot be maximum in motion. It is only maximum at a point. Maybe you can use the word increasing or decreasing. From point A to point B, what is happening to kinetic energy, if I may ask? Is it increasing or decreasing?
Increasing.
That is wrong. Are you sure when the body is moving up, it is accelerating? When it is moving up, which up is against gravity, that body is decelerating, meaning its velocity is increasing. Kinetic energy will decrease according to its formula. Then as the body is moving up, the value of h is increasing, and since potential energy is mgh, it will also increase. I don't know if you're getting the statements I'm making. Do you try to connect the physics?
Yes.
Hmm? Do you know
Yes,
the
doctor.
formula of kinetic energy and potential energy?
Kinetic energy is a half mgh.
mv squared. No.
mv squared.
Yes, now what is disturbing here are the formulae, but you need to understand them. All you need to understand is that for kinetic energy, it is a half mv squared. So this velocity means a lot. Then for potential energy is mgh. I don't know if people know those formulae. They are very important. What does that mean? That as height increases, potential energy increases. As velocity increases, kinetic energy does what? Increases. You get? And you people should know, when does velocity increase? Velocity increases. Okay, if at all you're having an increase in velocity, that means acceleration will also increase, because acceleration is the rate of change of velocity. So when velocity increases, even acceleration increases. You understand? Yeah. So when the body is trying to move up, it is moving against gravity. So don't expect that body to be accelerating. Its velocity will have to decrease. That's why we always say the body is under negative acceleration or deceleration. Deceleration means a decrease in speed. So when speed decreases, according to the formula of kinetic energy, even kinetic energy will do what? Will decrease. Then potential energy, it is mgh. It is mgh. That is the formula. H for height attained. So as the body is moving from A to B, the height attained is increasing slowly and slowly. That means potential energy will be increasing. And at point B, which is the maximum or the farthest point reached, we shall have the H maximum. And because of the H maximum, we shall have attained the potential energy maximum. And at point A, that's where we have the maximum velocity. Because at point A, where we have the maximum velocity, that means we shall have there the maximum kinetic energy. Why am I really explaining all this? Because the definition talked of the total energy of the oscillating system. So you need to know which energy are they talking about in this case. Because in the future, these things will come and you start hating the easiest subject for no good reason. So let me remove this. Okay. So now at that point, point B, potential energy is maximum. Then at this point A, kinetic energy is the one that is maximum. Yeah. The ones of minimum are those ones never bother. Point B is the same as point C. As simple as that. So that's what they call the energy of the oscillating system. So they are like, if it is amplitude, if it is the energy of the system, provided the oscillation is free, provided it's free, those two things are not going to change. They are going to remain constant with time. They are not going to change. So what are those examples of such kinds of free oscillations? The very first one is what? A mass held on a spring and oscillating in a frictionless medium. Why they are saying frictionless? You know that friction opposes what? Friction opposes motion. I just want you to understand this. I'm not going to write, but what you need to know that friction opposes motion. So if at all the medium is having friction or air resistance, that means we are going to lose energy. And when we lose energy, that means the oscillation is no longer free, because for the oscillation to be free, total energy must remain constant. But in case friction comes in, air resistance comes in, and it resists, or opposes motion, that means we shall not reach the highest point. For example, assume there is friction in this medium. That means if motion is opposed, we may not reach point B or point C, which are the maximum points. So if you don't reach the maximum point, then you may not attain the maximum potential energy. So that means you will have a reduction registered in potential energy. You get it? And when you register a reduction in potential energy, what does that imply? That implies that you have not maintained the total energy of the oscillating system. So it cannot be a free oscillation. I put a tick on that. Vibrations of prongs of a turning fork. Oh, sorry, tuning fork. Sorry. Tuning. I don't know if you people have seen a tuning fork before, because it is used so much. Who has never? You go to the internet right now. I told you for some things you'll be checking on the internet as I teach. Go to Google, put in tuning fork, single N tuning fork. Go under images and look at it. You'll see its prongs. The ones they hit somewhere, then it starts to vibrate. I think we are also going to talk about it in the future. Do I have anyone who has never seen a tuning fork? Because it is something very important in this subject. Very important. Let me see here. Tuning fork. Think people can have a look at it so that you see the prongs they are talking about. Yeah. You see, science becomes good when you know what they are talking about. Are you seeing the tuning fork? It is used mostly in medicine, yeah, to assess vibratory sensations. So that's how it looks like. I think you saw the person trying to hit the prongs down. That's another video.
Here's how to use a tuning fork in less than 10 seconds. Grip it, tap it, tune it. Here's how to use a tuning fork in less than 10 seconds. So we have two tuning forks. If I hit one, it makes a note. If I put them together and I hit one, it makes the other one ring. If I put this against there, and then I put this there, and I hit the tuning fork, we can make the ball move. That's science. So we have two tuning forks.
Who can tell me how that is called in physics? They tried to hit tuning fork 1, it made the next tuning fork to vibrate at the same frequency, and then the other tuning fork made the ball to also vibrate at the same frequency as the very first tuning fork. How is that called in physics? How is that called in physics? How do they call that phenomenon? How do they call it? Do you people know? Hey. No one knows how that is called resonance. Thank you so much, Haman. That is it. It's called resonance. They try to hit the very first one. You watch it again. The first one, it made the second one vibrate at the same natural frequency.
It makes a note. If I put them together and I hit... So we have two tuning forks. If I hit one, it makes a note. If I put them together and I hit one, it makes the other one ring. If I put this against there, and then I put this there, and I hit the tuning fork, we can make the ball move. That's science. So we have two tuning forks.
Yeah, hope you people get it.
When you strike a tuning fork with a mallet, it starts doing something incredible. It begins to vibrate hundreds or even thousands of times per second. A standard...
Now, I want you to take that serious because when I read things like wavefronts, when I read things like phases, there are things I'm going to reach and I will need this very same video. So I want you to look at it. That very one, just listen to what they say. In the future, I'm going to ask you and we shall not come back.
So we have two tuning forks. If I hit one, it makes a note. If I put them together and I hit one. So we have two... When you strike a tuning fork with a mallet, it starts doing something incredible. It begins to vibrate hundreds or even thousands of times per second. A standard tuning fork, like the one used to tune instruments, vibrates at 440 hertz, which means 440 vibrations every second. Those two arms move back and forth so fast that to the human eye, they almost look like...
That's what I wanted you to see. That to and fro movement, yeah? It's what they talk of as the oscillation. Have you seen the to and fro movement? So you can look at the tuning fork and be like, now where are the oscillations? Where is the to and fro movement? It comes after you've what? you've tried to hit it.
Like they're moving in slow motion. That's not real slow motion. It's just an illusion caused by how fast the metal is oscillating. Each tuning fork produces its own unique note depending on its size and the material it's made from. It was once used by musicians to tune instruments, but now it's also popular in sound therapy and meditation for its calming tone. When you strike a tuning fork,
Yeah, that's enough. So hope you people have tried to learn something at least. Yes, now let's go back. So you've realized the transfer movement that comes. Of course, what are they saying in a vacuum? So you people, it's very easy. In a vacuum, we have no matter. You all know that vacuums are matterless spaces. So when we have no matter, that means we are not even going to have things like air resistance. Let me hope people are aware that air is matter. Air particles. Yes, they actually have mass, they have weight. So if there is no matter, that means there is no air. If there is no air, that means there is nothing like air resistance. But if air resistance was there, that means the vibration could be interrupted with. You get? Then here they are talking of movement of a frictionless piston. So the most important things here are frictionless, vacuum, frictionless. We are all trying to do is to avoid loss of energy that may be due to friction, due to air resistance. Another one, there are oscillations of a pendulum bob, what we've been talking about, but strictly in a vacuum. That's why I had to bring it generally as an oscillation. But it's only free if at all you're doing your things in a vacuum or in a frictionless medium. But in case the medium is having friction, or in case you're doing it in air, you may find out that it may again be a damped oscillation. And let's introduce damped oscillations there and then. So it is the damped oscillations are the exact opposite of the free ones. So when you look at damped, what are they telling us? They are saying, these are oscillations where the total energy decreases and also the amplitude decreases, of course, with time. So just like the word says damped, you can easily understand that the change here is a decrease because damped is an English word. And of course, you can't expect it to be meaning an increase. So this time around, the energy and the amplitude are decreasing. And I told you the things that may bring about the decrease, friction, not doing things in a vacuum, and you end up having air resistance to bring everything at a stop. You understand? Now, the very first example I want to use is I don't know whether you people have visited banks and corporate toilets. You know these normal toilets. Do you know these doors that always have the word pull or push? When you pull, it is not you pushes it back. It pushes itself back. If it says push, then you push. It's not you pulls it back. It actually does that on its own. That is an example of a damped oscillation. Yes. Because, and trust me, if the damping wasn't there, that door would keep oscillating just like these normal doors. These normal doors, if you don't close it, realize because of doing it in matter, for example in air, because of the things of air resistance and so on, it can easily be moved. So it just keeps oscillating like that, even if the oscillation is minimal. But those doors of banks and toilets and offices, the moment you push it, it pulls itself back. That means there is some external energy that is trying to minimize the oscillations. Something like that. So for you just understand one thing, it is the exact opposite of the free ones. Here they are talking of gun mountings on ships. I don't know if you people know this. When you fire, or after firing, of course that's the gun releasing a bullet. I know that you are aware that the gun recoils. And when the gun recoils, we have what we call oscillations. And when oscillations happen, For the gun to return smoothly to rest, damping must happen. Because you fire a bullet, we have a recoil, the gun oscillates, but then we must bring it back to rest. That is what they call damping and oscillation. So if we just understand damped oscillations as bringing oscillations to a stop and nothing much. Like I've pushed the door, but they are going to bring it back to where it has been. That's what they call damping. So assume the push has been the oscillation, and now they are trying to damp the oscillation by bringing it back. So in the due course, as it is coming back to the rest position, so where it has been is the rest position. And you all know that as the body tries to go back to the rest position, amplitude is decreasing. And you like it or not, even the energy of the system, which is basically potential energy, it will be decreasing. Very obvious. You get? Then shock absorbers. You all know that in case a car hits a bump, yeah, I don't know whether you people are aware that in cars, in the system that moves the car, we have so many springs. You get? And I don't know whether you're aware that shock absorbers create friction. And I don't know whether you are aware that in case friction happens, we lose energy, mostly as heat. I don't know whether you people know that. And you all know in case we have a break by a car, we always have oscillations dying out. I don't know if you people are aware of all that. But all you need to understand, just get one example and get to know the meaning. But because of the word damped, we expect these things to decrease. How do they decrease? That after displacing them from the rest positions, they are brought back. For example, the doors we push and they automatically come back on their own. The doors we pull and they automatically get back to where they have been. Firing a bullet from a gun and the gun recoils and oscillates, then it goes back smoothly to the rest position where it has been. You get things like that. And we also have loss of energy, because you are aware as amplitude decreases, you are trying to reduce the maximum height you can reach. You're reducing potential energy, so there is no way the total energy of the system can remain constant. It will have to change, and of course the change is a decrease for the very reasons you know. Concerning the moving coil galvanometer, that one may not overstress you right now, but we shall see it when we reach current. I will explain very well. So that is it. So in your free time, you can add on your own research and get more differences between damped and the free ones. Yeah, the damped and the free oscillations. Okay, hope you're taking note. So we have those ones that are forced, but these that are forced, I don't want us to waste a lot of time on them. I don't want us to waste time on them. But by forced, we mean they always need an external force. Just listen to what I'm saying and take that. So by forced oscillations, what do we mean? They always need an external force to keep them moving. As simple as that. Forced oscillations, you are forcing oscillations. To force an oscillation, you need an external force to keep the system oscillating. Period. Nothing much. But don't worry, I'm going to provide this book immediately after the class. Wait, you people, you've not been seeing my screen? Have you been seeing the screen? What have you been seeing? Because they brought me a notification to continue screen sharing. Did you see this? Did you see me trying to show you the definition of forced oscillations? Did you see them?
Yes.
Hey, okay then. Thank you, Jovan. So I'm saying that these are oscillations where the system is subjected to a periodic force that's setting a system into oscillation. You get it? The force is periodic. What does it mean? That you apply the force and after a certain period the system stops oscillating, and then you're supposed to come back and force it again. after a certain period, it stops, then you're supposed to come back and push it so that you keep it in what? In motion. That's what they call forcing. Yeah. Okay. Now I want us to go to waves. Now we are introducing them. So I want you to understand that a wave is not an oscillation. A wave is now something different. So you all know what waves are. And I don't want you to forget this thing. You know that that's how water waves move, and that's how you always show waves in physics. Don't forget that thing. Let it at least be always in your mind. Always let it be in your mind. Never forget it. So what are they saying? That a wave is a periodic disturbance that travels with a definite velocity through a medium. Yeah. And the other thing you need to know, that with a wave, this medium has particles, because the medium can be solid, liquid, or it can be air. So this medium has particles. The things you're supposed to know. So what you need to know about these particles, they do not move. They will never move. So I'm saying they do not move. But what you need to know about them, not only just understand that they don't move, but they vibrate. You get? And when they vibrate, of course, energy is generated. And in the due course, the wave transfers energy. You know that you people are getting it. So the particles in the medium never move. But what do? They vibrate. And when they vibrate, energy is transferred. Like that. Energy is transferred. So here they are talking of an assignment. They want you to distinguish between a wave and a vibration. So this is it. When the disturbance travels with a definite velocity through a medium, before it even travels, the disturbance that occurs makes the particles of the medium to vibrate. When the vibration occurs, we are going to have transfer of energy through the medium. So that path followed by the energy transferred gives us a wave. Simple as that. Hope people try to get something. Disturbance happens, particles vibrate, energy transferred. That path of the transferred energy is what comes up with a wave. Something like that. Yeah. So they are saying if it is a short-lived single wave, it is a pulse. Then if it is a continuous group of waves, then it is known as a wave train. Let me give you a very simple example. Maybe what you can recall with time and not forget. I don't know whether you people know a rope. So assuming you're having a rope like this. So I'm going to use two ropes. So I can get this rope, and I don't know whether you people know what they call a jack. So I can give it a quick jack at one of the ends. For example, at this left end here, I can give it a quick jack, and on giving it a quick jack, this happens, and then it goes back to its normal position. That's after a quick jack. You be like, you try it as if you're pulling it a bit, a quick jack. Then there is me giving it a jack at this point, or a strong jack. And then after this happens, I don't know that you people are getting me. So in case the jack is very quick and slight, we are having a single wave. I don't know that you people are getting me. So that single wave is what they call a what? A pulse. But in case I give it a serious jack here, in case I give it a serious jack, this is going to happen. Are you seeing that? And you can see that that is a group of waves, or what they call continuous something. It is a group of single waves. So now that's what they call a wave train. So that's what they call a wave what? A wave train. So I think you can see here that if it is a short-lived single wave motion, that is a pulse. If it is a group, then it's a wave train. So you should know those terms. Then the other one is just a definition of waves. So they are telling us here that we are basically having two waves, or forms of waves. There are those waves that are mechanical. There are those waves that are electromagnetic. People, there are things we are going to understand in this topic, and I don't want you to be disturbed. I don't want you to be disturbed. There is when we say mechanical versus electromagnetic. There is when we say progressive versus stationary. There is when we say transverse versus longitudinal waves. So you should be knowing all those things. There is when we say mechanical versus what? Electromagnetic. There is when we say progressive versus what? Stationary waves. There is when we say transverse versus longitudinal waves. But all you need to know that these two, the transverse and longitudinal, those are forms of what? Progressive waves. Don't even waste your time. Just take it like that. Then have it in mind, for mechanical and electromagnetic, the difference is very simple. That for mechanical, for them to be transmitted, we need a medium. For electromagnetic, as you hear them, we only need electric and magnetic fields for them to be transmitted. So these ones are always about the medium of propagation. Then for transverse and longitudinal, we shall see. They look at the direction of wave travel. They look at the direction of what wave travel, and it's strictly progressive. Then we shall see the stationary waves. Those ones are on their own. And basically, progressive and stationary, the difference is in how they are calculated for. So you should have that basic knowledge. I don't want to waste a lot of time there. I believe it's not so disturbing. Okay, so there are those basic two waves, and they are considering the medium of transmission. The moment we read any statement and it doesn't make sense, you please ask immediately so that you're saved. So they are saying, so you need to know how these electromagnetic waves are produced. I don't know whether you people, so I don't know whether people got now what a vibration is. Hope you got the difference between a vibration and the wave. So it's a vibration first, then later we can come up with a wave. If particles do not vibrate, imagine the particles of that rope did not vibrate. That means we couldn't come up with those groups of waves to form a wave train. So it is vibration first, then a wave comes up. Because vibrations give us energy which is going to be transferred. And that path of transfer is actually the what? The wave. So now I want us to look at what we call the magnetic and electric fields. You may ask yourself, where are these things? These things are in space. So have it in mind, the space is having the magnetic fields and electric fields. And of course, we have charges there. So when these charges oscillate in one way or the other, that's when energy is produced and we end up transferring it. And that's how electromagnetic waves come up. I'm not going to write this, I've just said it. And I repeat, in space, including vacuum, what do we have there? We have the electric charges, if I may say. We have their magnetic poles, which magnetic poles will give us magnetic fields. Even electric, I can say electric poles, the positive and negative. Then, of course, you know what gives us the magnetic fields. You know the magnetic poles, it is the north and south poles, depending. Those two bring about the electric fields. The positive and negative electric poles give us electric fields. The north and south poles give us magnetic fields. And those fields have strength. What we call the electric field strength and the magnetic field strength. You need to know those things. You need to know those things. And when you reach things of electromagnetic induction in electromagnetism, you will understand more. That's why I don't want to go into details, but just listen to this. So, when we happen to have, for example, the electric charges accelerating or oscillating, if I may say, that is simply their movement to and fro, of course, from their equilibrium position. So when those oscillations happen, you know, we shall, of course, have transfer of energy. You get? And when transfer of energy is happening, of course, we cannot hide from a wave. And that's how electromagnetic waves come up. So how do you define them if you ask to? Just say those ones are produced by the electric and magnetic field vibrations. And you should understand that these vibrations happen at very high frequency. So very high frequency is the keyword there. All this information I'm giving you is very clear in my favorite textbook, Neocon and Parker. It is my favorite for electromagnetism. That's where the content is. But as far as waves are concerned, I prefer Tom Duncan. Yes. And if you really want those books, I know many of you have them. You please share them in the discussion group. If none of you is having them, immediately after this class, ask me to send. Once in a while, visit textbooks. Feel the A-level vibe. Don't be these people who are going to leave A-level and you have no story to tell. That we once read textbooks, we once never understood textbooks. So be part of the game. So these electromagnetic waves, I've given you the story, and I'm not repeating it. So what is this not saying? They are saying there are no particles involved. That is very important, because I began by saying these things are happening in space, including vacuum. But have it in mind, no particles what involved. The reason as to why they are grouped with mechanical, because for mechanical, as we hear the word mechanical, we need a medium for them to be propagated. But for electromagnetic, even the way it looks like, it's like we have nothing mechanical involved. It is purely vacuum. So they are saying no particles involved. So for an electromagnetic wave, we do not require a material medium for their propagation, meaning they can go through a vacuum, because a vacuum is a mediumless or matterless space. You get it? Yeah. So they are saying that these electromagnetic waves traverse, transverse, and travel at the same speed. That is very important to note, at the same speed. And we are going to see that their speed is very high. Why is it very high? The vibrations that bring them about are happening at very high frequency. So those are already 2 points and very important. So we have now what we call the electromagnetic spectrum. And the electromagnetic spectrum, have it in mind, it is the gasovira. That's how I understand it. The gasovira. Ga-zu-vi-ra. Like that. Ga-zu-vi-ra. So the Ga is for the gamma rays. And gamma rays, you know, that is the formula of gamma, or the notation of gamma. Then this capital X, you all know. X-rays. Yes, Richie? Yes, Richie, unmute. As if you had something to say.
Dr. Gleason, Dr.
Give it.
Gleason, my concern is about, maybe you clarify more on waves. The electromagnetic waves are transverse and they travel at the same speed. clarify on the term transverse. I'm not getting it clear.
Oh, I think they wanted to say you go to the internet right now. You go to Google and ask for the meaning of the word traverse, because that's the word I said. What does traverse mean? I don't really think they were meaning transverse. Doesn't make sense. What is the meaning of traverse? Maybe I can answer you. Because this is not a textbook, I just organize notes. So for me, according to me, that word is not, it's supposed to be like that, traverse. What's the meaning of traverse? I think it's what they really wanted to mean. Let me also check the internet. But students will disturb me. Students will disturb me if I get online. You check very fast. You check very fast and tell me in the chat, what does the word traverse mean? Maybe you can understand. To travel across, exactly. I think that's what they really wanted to, that's what they really wanted to mean. That's what they really wanted to mean, because transverse is a form of progressive, as I told you, with longitudinal. So I don't really expect it to be transverse. You leave that alone. So back to the Gazuvira as the thing of the what? Of the electromagnetic spectra. Okay, let me brief you. When we reach progressive waves, we shall talk about transverse waves. Then as we look at the characteristics of the transverse waves, we shall see whether we shall see the characteristics, and then we shall see that among the examples of transverse waves, there are majorly three. There are waves in a stretched string, there are waves on water surfaces, and then there are electromagnetic waves, basically the light and radio waves. I've recalled something. When we reach transverse waves, we shall give light waves and radio waves as examples of as examples of transverse waves. But remember, the radio waves here are part of the electromagnetic spectra. So I beg your pardon. When we reach transverse waves, we shall see that radio waves are examples of transverse waves. But again, the radio waves here are part of the electromagnetic spectrum. That means radio waves are electromagnetic waves. So maybe I can also give the writer a benefit of doubt that maybe he meant transverse because of that reason. Because we shall see that transverse waves, I don't know whether people are aware that the particles always vibrate perpendicular to the direction of wave travel. And I told you we shall look at that. Then the key features, they are having crests and troughs. There is a possibility of them being polarized, and we shall see that in the wave nature or the wave theory of light concerning the polarization of light. And then we shall see something about waves. And we all know that energy is always transferred along or across the medium. Then when we reach examples, we shall see the waves on a stretched string, we shall see water surface waves, we shall see electromagnetic waves, but strictly the radio waves and the light waves, where radio waves are a form of magnetic ones. I don't know whether people are aware that even light waves are electromagnetic waves, because from the Gazuvira we have the V, which V means the visible spectrum, where we have the visible light. I don't know if people understand. So you can leave the traverse. Traverse is just a word to mean travel. We can leave the transverse part because of the explanation I've given. Okay. Yes, Jordan.
Good evening, doctor.
Good evening.
Hello? So I
Good
was
evening.
asking, electromagnetic waves don't require medium since they have no particles. So how is it so that light is made of photons?
What is a photon, if I may ask?
Because I know
You first define a photon before you tell me that. Did you study
I really
modern
don't
physics?
have. Hmm?
Did you study
Yes,
modern
but
physics?
I don't have the definition of photons. I know them as particles that make up light.
Oh,
They are
so
packets of
this is
energy
mm,
that
my
make up
first
that.
question. My first question. Do they have mass?
No, they don't.
Thank you so much. But they carry energy, not so?
Yes.
Do they have electrical charge?
No.
Thank you. So have it
Thank
in
you.
mind that the photons are only having what? They are just carrying energy. They don't even have mass. So the mere fact that they don't mass, that means they are not even real media. If they are not real media, then you ignore. Hope you understand. Have I answered you? Who is Jordan? Jordan, have I answered you well? Okay, so concerning the gas review, I told you about the gamma rays. Then we have X-rays. Then we have the ultraviolet light. Then we have the visible light. We have the infrared. We have the radio waves. So under radio waves, they added on the microwave radar, added on the TV waves, and so on. So what you need to know that in that direction of the Gajovira, two things are happening. Yeah, this is one of the facts in physics. Two things are happening. Yeah, that we are having a frequency decreasing and then wavelength increasing. You've been hearing this for some good time. I don't think it is a problem right now. And I just believe by this time, people must be knowing what exactly is happening. And you all know from the wave equation, the basic wave equation, which is, I don't know whether people know the basic wave equation. From the basic wave equation, which is velocity, lambda f, you can see that lambda is v over f, isn't it? So you just realize that wavelength is inversely proportional to frequency. That means as wavelength is increasing, frequency is what? Decreasing. That's what you need to know. As one increases, the other decreases. As the other decreases, the other increases. That is it. So you can literally understand this by considering these first two, the gamma rays and X-rays. From modern physics, at least you're sure that these ones have a very high frequency. That's why they can penetrate. That's why they can even be used in diagnosis, those X-ray scans and so on. Because of the frequency they have, they are good at penetrating. So when you understand that they are good at frequency, you'll be like, oh, that means they have the highest frequency. That means as we move from Ga to Ra, that is Gazuvira, frequency must decrease. And when frequency decreases, wavelength increases. That's how I used to recall it 10 years back as a student of physics. That the gamma and X-rays, because they are used in medicine diagnosis, getting what is inside your body, that means they are good at penetrating. That means their frequency is so high. And if they are coming fast in the spectrum, that means frequency must decrease as we go on and on, because they are the ones having the highest. And since wavelength does opposite to what frequency is doing, if frequency is decreasing, then wavelength must increase. And that's how I left the spectrum. I will go mechanical waves. Mechanical waves are already on the exact opposite of electromagnetic. For them, they need a medium. They need a medium. They need a medium. So we are saying are waves produced by vibrating particles of the medium. Are you seeing that it is a wave produced by vibrating particles? That's what I meant, that it is vibration first, then a wave being formed and are transmitted by the particles in the medium. I still remember telling you that particles in the medium do not move, but when they vibrate, we shall have a transfer of what? Of energy. So they are telling you they are transmitted by particles in the medium. For example, water waves. So water waves are transmitted by water particles. Sound waves may be sound in air. They'll be transmitted by the what? Air particles. Waves in plucked strings. Plucked strings are solids. So the waves will be transmitted by the solid particles in the plucked string. Simple as that. So you have examples, you know, definitions, and you know some facts. You can get the differences between the two. And there is that one textbook that is good at giving us distinctions between the different things in physics. Yeah. So you can see here they said, mechanical waves need material medium for propagation. You know, these ones can propagate in a vacuum. Relatively low speed. This one's very high speed. I told you already. You can see vibrations. They are due to vibrations in the medium. This side, you can see electric and magnetic field. You can see. You can leave out this one, not very clear, because here they are talking about speed, here they are talking about wavelength. So you can, that was an error. But of course, you know, of course, you people know this. Let me show you. They are talking of wavelength and speed. Yeah? So you should never be confused. Every time you're confused about the relationship between velocity, wavelength, and frequency, the wave equation should always come to your RCQ. Just like you saw above when I used it. I think I used it on that very thing of the electromagnetic spectrum. So it's not a big deal. Now, wavefront. I told you for today we are going to be covering these weird terms, These weird terms. So that in the future we are not disturbed. Okay. Now, before you even maybe watch a video on a wavefront, I'm going to first brief you. I'm going to first brief you generally. When you look at that definition we have there the word phase. We have there the word in phase. So if I may ask, do I have anyone who is live right now and knows what in phase means? When they say in phase, particles are in phase, what does that mean? Particles are in phase. Do I have anyone who knows that? Do I have anyone who knows that when they say the particles are in phase? I don't know if you people have just tried to maintain the number, but someone should tell me if you've been active. Has the number reached 40 or I saw badly? Has it reached 40 at any one point? Or I'm confusing it with some other lesson? Did the members try to reach 40 at least? Or they didn't? Someone tell me. Someone tell me. There are some of you who have not been giving me answers, but when I asked about the number, oh, you're very sober. You're even telling me that at one point they dropped very quickly. You people, you're not easy. Okay, let me first tell you this. I told you not to forget how a wave moves, generally, or basically. I want to show you this. So the phase is just like a stage. Stage of the wave. So if the wave is moving like this, are you seeing that? I can call this one the start, when it is just beginning, the start. I can call this the rise, because it is rising, of course. I can call this the peak, because if it has reached the maximum. Then I can call this the fall, because it is actually falling back, and then here it's going back to zero again. Back to zero. So what they call a phase in physics, what they call a phase in physics, here when it is starting, it is a phase, because that's a stage. Stage of rising is a phase. Stage of being at the peak is a phase. The stage of falling is actually also what? A phase. And also when it's back to zero, back to the starting point, maybe, it is still a phase. So that's what phase alone means in physics. Phase alone. But when they say in phase, so when they say phase, it is just one particle. Yes, one wave particle. I can say one wave particle. One particle. Yeah. But when they say in phase, you need to know these things. In the future, I will not repeat them. When they say in phase, it is now different. Okay. So when they say in phase, that means now the particles are two. Yeah. When they say in phase, the particles are two. Yeah. Now, why do you come out and say that now they are in phase? So I'm going to consider particle 1. Yes, I'm going to consider particle 1 with particle 1. Then particle 2. Yeah, like that. Then I'll come something like that, like that, like that. So what do we mean by particles being in phase? Being in phase. This is what it means. Two particles being in phase, that means they are doing the same thing in the same time. They are doing the same thing in the same time. They are doing the same thing yeah, they are doing the same thing in the same time. That's what in phase means. They are doing the same thing in the same what? In the same time. For example, if you're having those two particles like that, maybe we can try dealing with these ones. Maybe, I don't know if you people have heard of things like amplitude, displacement, wavelength, and so on and so forth. So for this case, the amplitude or the displacement, the vertical displacement may be something like that. Maybe something like that. Yeah. So if maybe here the displacement is, let me set 2, whichever units. I don't want to put units. Just put 2 units. And also here we are having 2 units. What does that mean? That means that every time this wave rises, its maximum is 2 points. Every time it rises, its maximum is 2 units. Every time it rises, maximum 2 units. Every time it rises, maximum 2 units. And if it is the same for both waves, that means they would always do the same thing in the same time. Meaning that every time they decide to get displaced vertically upwards, they will have a maximum of 2 units as the amplitude. I don't know whether you people are understanding. That's what they mean in phase. Then the other thing for the in phase is the direction. You realize I was drawing them in that direction, left, right. So when they are having this direction and it is similar, we can say they are in phase. Then the other thing, for example, at that point, you can see it is in line with that point as well. So if let's say this is our scale of time, it may be seconds, this is our scale of time, it may be seconds, you get, and then this is maybe 10 seconds, maybe this is what, 10 seconds. So after 10 seconds, we reached the maximum point. You see, we reached the peak. Even here at 10 seconds, the same thing. Maybe we reached the what? We reached the peak. So what is happening? We are reaching, the two different particles are reaching the peak after the same time. That means they are doing the same thing at the same time. So we say that they are in what? They are in phase. That's what these things mean. So I don't know whether you people are aware that this is what they call a crest, because it is raised. Then this one is what they call a trough. I don't know whether you people are aware. Yeah, the other one that is raising is the crest. This one that is down is a trough. Can see it looks like a trough. Then the other one is raised, so it's a crest. This one is a depression. It looks like a trough. So the other thing of things being in phase, you can see that here this crest can meet with this crest. Those two crests can actually meet, or they are in line. Consider this crest is in line with this crest. You understand? Even this trough is in line with this trough. So if at all they are to meet, I don't know if you people can realize that the other crest will just come and cover this crest, then the other trough will come and sit in this trough. That's what they mean by in phase. A lot of things in common happening simultaneously or in the same time. So in phase, I don't expect in phase to be a very bad or a very disturbing word. So if you understand the in phase, then you've understood what we call the wavefront. Because now the wavefront is just joining all particles in the same phase. So assuming that these particles that are in phase are twins, and then you get a place that is going to collect all twins in Uganda. So the twins looking alike, that's what they call in phase. Different twins coming together in one place, that's what they call a wavefront. So a collection of all particles that are doing the same thing at the same time, or a collection of particles, wave particles that are in the same phase or that are in phase, is what they call a wave what? A wavefront. Yeah. So make sure you know that simple physics. Yeah, so we can now read it. What are they saying? They are saying it is what? It is a section through an advancing wave on which all particles are in phase. I want you to read here. What are they saying? They are saying read on types of wavefronts and comment on the relationship between the distance between successive wavefronts and wavelengths. And this is very obvious. You look here. I'm going to use red color. I want you to look at this particle. Okay, the first wave particle at that point, it will have the same behavior as particle 2 at that point. So my question is, when exactly will the wave particle 1 have the same behavior Imagine this is at point A. You people, I want you to tell me the fact. This is point B. This is point C. This is point B. I want you to tell me. I want you to tell me. I'm on wave particle 1. Yeah? So wave particle 1 at point A it's having a certain behavior. At which other point will it have the same behavior? What do I mean? That at that point A, it is going down immediately after it. So at which other point will the same wave particle A have the same behavior like the one it's having at that point A? Exactly, point C. Because I think you also see that at point C, it will also now be going down. You understand? So I'll come here and say point C. So I don't know whether you people are seeing the distance between point A and C. I am aware that that is the wavelength because some of you have revised these things. Do you see that the distance between A and C is the wavelength? Are you aware the distance between A and C? You look at it well. Are you aware a combination of a crest and a trough, their length is equivalent to wavelength? Are you aware? Good. We are very few, provided one student But sir, you're saying that the particles don't move. I'm talking of the wave particle. It is the path of the wave. So I'm talking of the behavior of the wave at point A. Okay, you leave the word particle. You leave the word particle, but look at wave. I'm talking of the wave only. But to put particle is just trying to be a wise-acting physics student. But even when you just say wave, it is okay. But I'm talking of a wave particle. So at least agree with me there. Okay, now between A and C it is wavelength. So here, don't gun read. I've helped you. I've helped you. So the distance between successive wavefronts, I think you've seen, and wavelength, they are equal. So wavelength is equal to that distance between successive wavefronts. Yeah, by successive wavefronts, I've described it for you as when else, like at which other point is the wave going to behave the same way like it behaved at point A. So someone could be like, even at point E, if at all I put here E, so someone could also say that even E, but even here they said successive. Yeah? Successive meaning you're supposed to consider the nearest possible point, which was C. So the E comes later, like that. So that's about a wavefront. When you find it in Roger Muncaster, you will understand it very well. So, concerning these properties of waves, you're supposed to just understand them by heart. They have explanations, but you may not need the explanations. And we shall also talk about them in so many other things. We shall be coming across them. So, why I wanted them to be in this lesson 1, so that if we meet them in the future, we are not disturbed. So, the first property of waves, it is reflection. And you can see that here our surface was a plain one. Even when it was tilted, it doesn't remove the fact that it is plain. I don't know whether you people are realizing they come like this, a straight line, and they leave like this. I don't know if you people are seeing that. Hey, very serious. Our plain surface is there. So they come like this. You get? Like this, like this. Every wave that falls, it just goes off like that, like that, like that. Hope you people understand. Hey. So here, just look at the structures and see what is happening. So the straight waves on a curved one. What are they talking of here? Straight waves incident on a concave circular reflector. So they are talking of concave. You people, concave, I remember teaching you concave. Because of this word cave, it must be curved inwards. You all know curves are curved inwards. A curve is always it's always something but inside, inwards. A curve, so concave or is curved inwards, as you can see there. So what do you realize here? They are coming as straight waves, but they are leaving as concave ones as well. You see, our reflector was a concave one, they came as straight one, and what happened? They left as concave ones as well. So that's about reflection. Just need to repeat these structures over and over and over. No big deal. Then you see here, still straight waves, but this time around is convex. So convex means curved outwards. The opposite, curved outwards like a forehead. Curved outwards like a forehead. So when they also come as straight, they leave. So curved outwards like the forehead, like that. So they leave as convex also, curved outwards. That is physics. These ones you just learn by heart. I don't think you have any option. Otherwise, you may run mad. So the curved ones, but instead on a straight reflector, you can see they came as what? They came as maybe concave, and they left as convex. You see? They came as what? Concave. Then they left as what? Convex. Hope you get it. We go. What of this one? So they are curved, and they also come into a curved reflector. They are coming to a concave one. They came like this. Hey. But they were bounced back as straight ones. I think you can see how funny the thing is. This F is just trying to show us the source of the vibrations. So the thing, you should just befriend those. Just befriend them. Don't be like, but why? Why is it like that? Don't overthink, just befriend whatever is happening. They are not much. They are around 6. When you get them, you're good to go. So, about refraction. So let me first test your physics in refraction. So, I want you people to tell me this. If someone answers these things correctly, I'm going to give you some money. And I want you to raise up your hand immediately. The moment you delay, that is malpractice. They are saying that when a straight wave front, you know what it means, crossing to a denser medium, that means it is crossing from less dense medium to more dense medium. They are saying speed of the wave decreases. I want you to tell me why. Raise up your hand immediately. Wavelength decreases. I also want you to tell me why. Then frequency remains the same. I also want you to tell me why. Okay, John Mary. Yes, tell us, John Mary. Give us content.
The speed of the wave decreases because our wavelength reduces. It's going
You're
to
saying John Mary, you are a liar. What is happening to other people with their hands up? You see? You're not serious. Not serious. You raise up your hand, you get defeated, you mute very fast, and you run away. Hey, things are not easy. But anyway, when they say to a denser medium, you all know that denser media have closely packed particles. So you listen a bit. You also learn this. In a denser medium, particles are closely packed, so it's hard for waves to travel. It's hard for waves to travel. It's hard for waves to travel through a denser medium. Hence, speed of wave decreases or reduces. Yeah, these are things you're supposed to be knowing. Very cheap things. So you now know V decreases. So we now know that speed of the wave, which is V, decreases. Yeah. Then the other thing you're supposed to know, that moving from a less dense medium to a denser medium doesn't change frequency. You should also know this thing. Doesn't change what? Frequency. Because frequency depends on the source. Frequency only depends on the source. Frequency only depends. Yeah. And now let's talk about, so what does this mean? F is constant, because you know frequency is F. So I'll say F is what? F is constant. So the one remaining is wavelength. So we are going to use the wave equation. Remember I told you to always come through. So I'll come and say from V lambda F, like that. What am I saying? This one is a constant, so it's not changing. So if it's a constant, what will that mean? That when V increases, then also lambda increases, like that. Then the reverse is true. The reverse is, remember, F is a constant, that when what? When V decreases, then also wavelength will reduce. Yeah. Then that means therefore this is wavelength reduces as we move to a denser what? Denser medium. So you shouldn't forget those things. I wasn't very happy when someone began with wavelength. That was a disappointment. Even when you begin with velocity and immediately go to wavelength, I will be very unhappy. First tell us what happens to velocity with the reason, then also tell us what happens to frequency with reasons. Then after, you can now connect to the last one, which is wavelength, like that at least. Yeah. So I think these ones are now very okay points. Yeah. Now this is about refraction. Refraction is the easiest. Of course, it will be done at the curved boundaries. And you can see they came as straight, the boundary was curved in that way, and they also left in that way, like that. Then when you look here, they came as straight, they made such a boundary. So this is what they call, so someone tell me, what name is given to this lens? If at all okay, even if I don't say lens, but which one is the concave, which one is the convex? That's what I want to know. The first one is the what? You're going to see people struggling. Even if I don't say lens, if you just tell me which one is the convex, because they just said, where is the convex? Where is the convex? Where is the convex? Okay, so the first one is a form of, convex, because you know convex is like this, the complete one. That's convex, So when I say that the first one is a form of convex, hope you understand. Then this one is concave. Yeah, thank you for knowing the shapes at least. We can move. So they are telling us to explain using the plane wave fronts. Let's explain why the convex lens. So they finally call them lens. So here they have used the full one. They want us to explain to them why they are the ones that are converging light. So this one was very easy. You realize this is glass, because they are lenses. So this is glass. That means we are talking, of course, of light. It is light that is traveling. So because this is glass, the light will move at a very low speed in glass. And when you realize at this point B, this car distance is very thick, compared to this car distance above in A. So that means here light will move very fast and it will leave. But then a lot of time will be taken for light to move through that thick part of glass for it to reach this. So because of that, we shall end up having our first wave being curved like that. We shall have it getting curved in that way. And that's what they call curving inwards. It will curve inwards. And when the inward thing continues and continues and continues and continues and continues, that's what they call converging. So use the same reason for why the concave will end up diverging light. You know, they are getting something. They are saying that here on top, this is point A, this is point B. This is glass, and because glass is denser than air, the light will be traveling at a very low speed. So by the time the light reaches this point, from A, we will have reached this point because the distance to travel through the prism or through the lens or whatever is very less. that means our first wavefront will be curved inwards and we shall end up converging light. You get? It's like have that point, and this point. The same thing with C. For light to move from that point C through, this distance is very short. So we shall very fast reach this point. But from B, this thing is thick and light will be moving at a very low speed. That means by the time we reach this point A and this point C, point B will be here. And when we plot, we shall come up with a wavefront that is curving inwards. And as we continue with the inward stuff, we shall end up converging what? Converging light. Something like that. So use the opposite reasoning to find out or to explain why for the concave ones, they will converge the light. Sorry, they will diverge the light. I beg your pardon. So that is it. That is it. That is it. That is it. Look at this question. They are saying, explain why sound waves from a distant source are more clearly heard at night than during the time. This is about refraction. This is one of the application of refraction. But this one shall be repeated under sound waves. This one shall be repeated under sound waves. Because we shall look at transmission under sound waves. And that's when we shall also talk about the moon. We shall talk about sound transmission at the moon. I don't know whether you people are aware that at the moon something funny happens. I don't know if people are aware that something at the moon, something funny happens at the moon in terms of sound transmission. Why the use of radios and so on are the ones that are recommended on the moon. So we shall look at such explanations. So explanations right now shouldn't bother you. But since that is an application of refraction, what you need to understand now is the refraction. Then other things will come later. So we shall repeat that under refraction, but of course, when we reach sound waves, yeah. This is another application. They are saying, explain why radio wave reception is good at night than any other time of the day. Then there is also why they recommend communication using radios at the moon. Okay. Now the third property of waves is diffraction. So diffraction, this one is very obvious. This one is very obvious. We just want to understand that if at all a wave is coming and it meets a gap or an opening, how is it going to behave after it has passed through the gap? That is it. That is it. So understand one thing, that these waves always spread. The moment a wave comes, it finds a small opening and it passes through it. The end result is what? It's spreading. So it usually depends on the size of the slit. So you can see that this slit is smaller and this slit is what? Is wider. So here they said narrow aperture, here they said wider aperture. So I don't know whether you people are saying where diffraction is actually greater. When you look at here, there is a way they are spreading in a way that they may even later die out. But they are telling you that diffraction is greater when the aperture is narrower. I think you can see when the aperture is smaller, that's when the diffraction is actually stronger. You can see. But when you look at these waves, they are like Tezilina man. There's a way they look, they're almost straight, they are not so curved. Yet we expect them to spread as curved waves, but it's not coming out as expected. So diffraction, waves spread after they pass through a small opening. But the smaller the opening, that's when the diffraction will be greater. The moment you widen the opening, then you're interfering with the diffraction. That's what I may say. Okay, now, The thing is interference. It is now another property of these waves. Another property of waves. People, when I reach these things in the future, I may not talk about them. So please make sure you understand. Yes, Richie? Yes, Richie?
Doctor, maybe you first scroll back up. Hello?
There?
Can I take this? Can I take it in the perspective of like the way we've answered the Gundi for the lenses for the case of the lenses, in that for the wave
What?
in the middle, it takes a long time to penetrate, and at the tips it takes a shorter time. Can I take the same perspective for this case?
And you explain it how? You tell us, we hear.
I explain it in a way that in this aperture, in this space that is left, the wave will take a shorter time to spread out, and by the time it spreads out at the other parts where we have the barriers, it will bring out this shape here.
Yeah. Provided it brings out the real physics, you can now understand. I usually call that local understandings, and I usually give them to you. Provided what your reasoning is, provided your reasoning is in line with the real physics, please always take it on, because you know it will help you make the real physics resurrect. You understand?
Yeah.
Okay, that is good. Okay, now let me first give you some story about interference because it is in this very point of interference that I'm going to give you research work. You can make research, because the next things that are coming after waves are calculations. This is the most boring part of waves, because we are supposed to just make sure things make sense, those basic things. The moment you see the word progressive waves, every definition has a formula. Everything we speak must connect to a calculation. So there are things will have become serious. So supposed to be ready. So when two or more waves meet, you need to understand at any point in space, they combine their effects. And when they combine their effects, that phenomenon is what they call interference of waves. So it's not a must that there are supposed to be only two waves, they can be two or more. So that phenomenon, we always use the word overlap. So when they overlap, they always produce a resultant wave. But you need to know that as they combine, it depends on how they have combined, and it depends on the resultant wave that they have produced. And then that resultant wave they have produced is what will help us to determine the amplitude. So have it in mind that in interference, what is happening? Waves are meeting. They can be two, they can be more. And they are combining their effects. And that combination is what they call overlapping. Since they are overlapping and combining, a resultant wave comes up. The resultant wave can either bring about an increase in amplitude or a decrease in amplitude, depending on how they have combined or overlapped. You get it? So you need to know that this interference falls under what we call superpositioning in waves. And we shall officially see the principle of superposition under stationary waves. So I think we are going to first watch the last video of this lesson to do with interference, so that when we come back here to give the last theory, we are just perusing through. We just have one page, I think, to end this lesson, if I'm not mistaken. Let me see. We have that one. We are also going to go through that explanation, sorry, that demonstration. These ones of speed of sound, those ones, I think you can see. Just one page, then we reach progressive waves. And this is where I'm stopping, and I'll give you a research So the moment we reach progressive waves, you can see, after leaving these things of transverse, are you seeing those terms used? Wavelength, amplitude, period, frequency, has, relationship between F and T, the wave equation, straight away to calculations. Even these things, you can see they are having equations. Intensity, inversely proportional to the square of what? Of D. Those things. Hey. Immediately you can see only calculation. They even brought in simple harmonic motion there. And then after that, we immediately go to calculations. Even after covering the longitudinal waves, we shortly talk about stationary waves, we now go immediately to the progressive wave equation. You can see it's having some sign, some trigonometry, just a few things, and then immediately examples. And after finishing these examples of progressive, we go to the principle of superposition, which takes us to the stationary wave equation. You get the one which has factor formula. And then after that, we now begin calculations there and then. And the moment calculations get done under stationary waves, we go to the sound waves. You see? And after covering sound waves, we shall be done with wave 1. The other side, the other part of wave physics will be the wave nature or the wave theory of light. Yeah, where we find you can see the Doppler's effect is this side. Yeah, and it is also just formally calculation and just that. So this has been the boring part of waves, but you need it. So I think you can see when all these things are done finally, you're going to see the wave nature of, this is vibration of air in pipes, this is in closed pipes. But all these things are not hard. I think waves are fine. The problem is with mechanics. So I think anytime soon we should go back. This is waves in strings and pipes, and that's what concludes the wave 1. The other one is about the wave nature or the wave theory of light. I think it is just here. Yeah, there it is. There it is. It's here. The wave nature, wave theory of light. Very serious, where we talk about polarization, as I told you. Yeah, very serious part. If you understand this part very well as a physics student, you have a good head. Yeah, that's what I can say. So I think you've seen that we have a long way to go, but when we do progressive and stationary, this holiday and complete, of course we are going to complete. Maybe we can now attack some other topic. Knowing that, I've left you with sound waves. You can't struggle because for them they are not so hard. But for progressive and stationary, have it in mind, we are doing them and completing. Then also the circular motion, gravitation, and simple harmonic motion, we are also doing and completing. And that's the only work of Senior 6 Term 1. Then maybe we shall see how to diversify our physics drive by adding there more work in your absence, because you'll have to go back to school. Okay, so back to interference. So I was telling you we are done, and I wanted you to watch some videos here on interference. Let me see if we can find some interference. Whoops. So I'm going to share my screen. Hope you're ready to watch something, because we are done, but I haven't given you research work, which I never want to do. So let me see, discovering Lorentz transformation with Albert Einstein, Leonard Susskind, and Brian Greene. Okay, we are going to watch everything about interference. Remember, interference can be either constructive or destructive. But I just want you to listen to the physics these people are going to be saying. Just listen to the physics. Okay, interference of waves. So let's watch. I don't know whether people are understanding this video. This video is showing you that for constructive interference, remember they are overlapping, they are combining to come up with a resultant wave. With constructive, the crests are in touch with crests, the troughs are in touch with troughs. So we can come up with something final. But with destructive, we are seeing the crest coming or joining a trough. We are seeing a trough joining a crest. Very disturbed, very destructive and disorganized. You can have a look at it once more. And I think you can see as they are showing the directions of those two waves, they are showing you that they are in phase. Those lines they have on the x-axis, if I may say, the waves we are meeting those lines at the same time. So these waves we are doing the same thing at the same time. So it is okay to say that they are in what? They are in phase. You see? You see? You're seeing the constructive and destructive interference in real life. So the other thing I want you to see, in our notes they were talking of Simanya a maximal response, maximal something. I think you see when the interference comes in, there is when a bigger wave is produced. In this very thing they are doing, there is when a wire, when they meet like this now, a bigger wave comes. Now that one is constructive. But there is when a smaller wave comes, now that one is destructive. I know you people are getting that when these two waves meet and produce a maximal wave or a bigger wave, that is constructive with a bigger amplitude. When the amplitude is minimal or when it is smaller, that is destructive interference. You watch it again. I don't know where you people are seeing it, eh? Especially that second part when they show us the other girl, the other side. There is when they produce a very bigger wave when they meet, then there is when the waves become very small, where the amplitude is decreased and where the amplitude becomes actually bigger. For me, I'm enjoying this. For me, I'm going to watch again. So I'm talking of U8, it is on, at that point, you see? Are you seeing that bigger one? Then those are smaller ones. I don't know if you people can see. Here, it wasn't very clear. But the other side, there. I saw that bigger wave, that one. Now that's what constructive interference. Where the amplitude reduces, that is what? Destructive. We proceed.
Form of waves. Each light wave has its own wavelength, amplitude.
So listen very well.
We know that light travels in the form of waves. Each light wave has its own wavelength, amplitude, frequency, and phase. Now, imagine two light waves traveling through the same medium. When these waves overlap, they combine to form a new wave. This process is called the superposition of waves. Superposition happens when two or more waves interact. A special case of this is called interference. In interference, two.
Have you heard that two waves actually combine? That phenomenon is what they call superposition, and interference is a form of superposition. Now they are telling us about interference.
Two light waves with the same wavelength, frequency, and phase overlap. Interference is of two types. constructive and destructive. In constructive interference, the crests and troughs of both waves align. This creates a wave with maximum amplitude. In destructive interference, the crest of one wave meets the trough of another. This cancels out the wave, resulting in minimum amplitude. We know that light travels in the form of waves.
So it has just repeated, but I think you've heard that interference, you should consider waves that are coming with the same amplitude, same frequency, and so on. For constructive, the crest is meeting a crest, that the crests and troughs are aligning. That's what they have said. Then for destructive, the crest will meet a trough, and the wave will cancel, coming up with minimal amplitude. But where the crest meets a crest, we are going to have something like synergism in biology. You're going to just come up with a maximum amplitude, and that's constructive interference. I don't know if you people are trying to follow. Okay. Yes, I'm supposed to do that because I know some of you
Each light wave has
don't understand the English. So we are watching this for the last time, and then we watch the last one, and I leave you to go.
We know that light travels in the form of waves. Each light wave has its own wavelength, amplitude, frequency, and phase. Now, imagine two light waves traveling through the same medium. When these waves overlap, they combine to form a new wave. This process is called the superposition of waves. Superposition happens when two or more waves interact. A special case of this is called interference. In interference, two light waves with the same wavelength, frequency, and phase overlap. Interference is of two types: constructive and destructive. In constructive interference, the crests and troughs of both waves align. This creates a wave with maximum amplitude. In destructive interference, the crest of one wave meets the trough of another. This cancels out the wave, resulting in minimum amplitude. We know that light travels in the... All right, ready? 1, 2, 3.
Eh,
Let's get some...
you people, have you seen constructive interference? Have you seen that maximum amplitude happening? Then later on, the minimal ones came. I don't know if you people are enjoying this the way I'm enjoying.
All right, ready? 1, 2, 3.
That one. Then that is destructive, because now the amplitude is minimal. That is now destructive. But that first one that's happening is constructive. You're going to see. That one. Hey. I think you can see. That's how good physics is. I think, are you seeing diffraction? Are you seeing diffraction happening? Yes, you take a screenshot and show your friends in the discussion group. You tell them for us we are watching a movie. Yeah, I think that is enough for today. Yeah, I think that's enough for today. So let me hope you people have gotten the thing of interference. The videos have been watched. Let me hope people have been getting the information from them. So I'm going to just be reading. So they're saying this is the superposition of two coherent waves. So the word coherent, you make research. They told you that these waves should have same frequency, same amplitude, and so on. So they are telling you that we come up with a pattern of alternate regions of maximum and minimum intensities. You've seen those ones of maximal and minimal. You've seen them happening in real life. So they are saying consider two coherent waves moving in the same medium. Same medium, I think you people have been realizing they have been using the same rope or same thing. When one is at the other end, another one at this end. So assume that is the medium they are talking of. Same. They are saying at points where the waves superpose in phase, provided it is in phase. In phase meaning a crest meets a crest. I warned you about that already. A trough meets a trough. What happens is called constructive interference. And there the intensity is maximum and even the amplitude that comes up is maximum. Then when it happens out of phase is when maybe a crest meets a trough. I told you that. What happens is destructive interference and their intensity is what? Minimum. Even the amplitude that comes is minimal. You get? Then that resulting permanent alternate regions of maximal and minimal intensities or amplitude is what they call an interference pattern. Yes, so that combination of constructive and destructive interference is what they call the interference pattern. So you take this because this is now an assignment, though you have the information already. But this is like a task. This is like the research. So go and read on the types of interference, the conditions, the demonstration, which I've tried to show you the applications, which you will understand. So that is the research on interference as our last part of today's meeting. Okay, that is done. Now here they were trying to show the demonstration of the longitudinal waves. It was easy. This is what these people did. They got two identical loudspeakers, L1 and L2, L for loudspeaker. They connected them to the same generator. You get? Then after they switched it on, and then they started moving this detector along a B. You get? And they realized, remember there are two. This is loudspeaker 1, this is loudspeaker 2. Of course, they are producing sound, isn't it? Then they got a detector of sound and put it this side. This detector of sound can even be a person. We just decide to connect it to our CRO so that we get to know the intensities. Remember CRO, the cathode ray oscilloscope, it can help us record those intensities as heights and peaks. You get? So they are saying as that detector was moving along a B, what did we realize? We realized that there were those regions where sound was very loud. Those are the ones of maximum intensity. Then those regions where sound was very low or very soft. And the difference in the intensity of sound is simply because of interference. Remember, there are two loudspeakers. So this one is giving you the waves, even this one is giving you the what? The waves. So where we are having overlapping in phase, it is constructive, so sound comes out loud. Where we are having interference or overlapping that is out of phase, that is destructive interference, so the sound has a minimum intensity, so it will be soft. And the combination comes up with the pattern we call the interference pattern. Something like that. You people, is this demonstration really hard? If they tell you to show how the demonstration is done, can you fail? Signal generator, the loudspeakers are 2. You have your line AB parallel where we put our detector, and as we move it along AB, we realize there is when we hear maximum sounds, and then when we hear softest sounds, then the loudest sounds. The loudest ones are because of constructive interference. When does it happen? When overlapping happens in phase. The softest ones happening for destructive. What do they mean? Overlapping happening out of phase. Out of phase meaning crest meeting trough. In phase meaning crest meeting crest, and trough meaning meeting trough. So just type in the chat demonstration, okay, demonstration, okay, demonstration, okay. Just type that in the chat. Demonstration, okay, demonstration, okay, demonstration, okay. Okay, now, these are things we shall find them. You may ask yourself, is this really an exercise to be done now? No. These are examples. They're asking you for the frequency of the source of sound. So these are calculations under sound waves. So it shouldn't bother you now. Yeah, even these ones. Yeah. To be done with time. Yeah, it will be done still in sound waves. Yeah, you can see sound waves. So it will be done under sound waves. Shouldn't stress you right now. Yeah, so even when I come and check this one, same thing, speed of sound. How can I talk about determining speed of sound using interference method? Of course, this one is also under what? Sound waves. Yeah, I don't want to bother myself, yeah, because of these things of 2FD. These things of 2FD come later, so you will be confused. But if at all you're there and you're a good student of sound waves, you can just read through. I said I'm providing this document after. So for you can just be like, I don't want to leave any page unturned. That's how I used to read those days. So for me, even when such things are skipped, I used to go back and force myself to understand. Maybe like, I'm not leaving this. But I just don't want you people to just cram this formula of 2FD. I want you to understand where it comes from, and that is only taught under sound waves. So I think you can see that we have officially reached progressive waves. So we have achieved today's target. So progressive waves, which were most of your concerns, it will be my next stop. Progressive what? Progressive waves. Okay, so when I come back here, I think I'll be very happy because these ones I'm done. So the last heading, this one has been achieved. I've given you the research and assignment. Yeah, so I can sign out. Thank you for attending, people. So we shall meet next time. So allow me sign out. Spol tutor. A tutor of math and science at Science Scholars Academy based in Uganda. Yeah. That's my number for WhatsApp calls. You're supposed to call me until I pick. Even if it's calling me for 4 days. Just make sure I pick. Or as you call, you leave a text. So I'm going to upload this lesson on our drive, but I told you in the future, we shall be finding all this information on our app. And I'll tell you the name of our app next year. Yeah, but it's there. So you now all know that our next stop, next time, they are progressive waves. You all know that when I give you the next stop, you please go and make research. So that you enjoy the next lesson. You're learning this in holiday. So when you make research and you come to me, you'll be learning it for the second time. When you go back to school, you'll be learning it for the third time. So, and what will make you fail? Progressive waves. Yeah. So today has been introduction. Make sure I've gotten every word that has been said. Yeah, to me it has been a success. Thank you for listening. Thank you for attending. And yeah, we meet. Thank you for the appreciations in the chat. I don't take them for granted. Otherwise, bye-bye.